Recently, I was profiling a component. On one side, it looks like this, accepting messages that are delivered to an abstract base class, one function for each and every message type. On the other side, it wants to re-emit these messages into a threaded pipeline via a concurrent queue. So we're trying to take heterogeneous types and map it into a single homogeneous type, which immediately makes us think of STD variant. Of course, that's what the original author of this component used, a variant with an alternative for every message type. But if you've been paying far too much attention, you realize these aren't the same message types because we need to do some mapping. We need to lift some transient memory into objects that actually manage it as it goes down the threaded pipeline. So we can, of course, solve this problem the way we solve every problem in computer science. We can just add another layer of variants, a type for the inputs and a type for the outputs. We can take the output type and we can stick it in a struct next to the session which emitted it, and that can go down our pipeline. We can take a look at the glue code implementation that goes between them. We have a handler that derives from our abstract base class and implements all of its functions by just calling a helper function. But note, when it calls that helper function, it doesn't just pass the message, it copies it into a variant. Then that helper function moves the variant along, combined with a session pointer, into a pure virtual function, the template method pattern. At the bottom of the slide, we can see the actual implementation. We default construct an update. We set the session pointer. We visit the input variant to set the output variant, and we move it into our output queue. By my count, that is 6 operations that we're doing here. That's a lot of operations just to perform this remapping. But if you look at the slide, you look at the code, we're using C++11 move. So surely everything is fast, right? But then we actually look at that variant. We ask the compiler to print out its size, and we realize it's over 2 kilobytes. A test run of this application takes 8 hours, but the application it was trying to replace only takes 4.5. So we need to go back to that list of operations and see if we can maybe eliminate some of them. Let's eliminate the ones that are downstream of that call to message. The first thing we're going to do is just get rid of that needless two-phase initialization by restructuring this type, not just to allow people to not two-phase in it, but to require it. Require them to initialize it by passing the things they actually want stored therein. Of course, this makes my implementation of message no longer compile, so I need to refactor it to eliminate those other 2 operations. So I'm going to switch to using emplacement construction into my container, and then I'm going to go ahead and use elide to take advantage of C++17 guaranteed RVO to make sure there are no copies or moves on this slide. And this technique of using C++17 guaranteed RVO is interesting, and I discuss it at length in my recent C++ Now talk, which for the last week has been available on YouTube. So I suggest you go and check that out. In the meantime, we're back to the profiler, and we're down to 6 hours. 25% of the runtime has been shaved off with these simple transformations, so let's hope we can get similar gains by just looking at the other 3, by going into the implementation of handler and making it more efficient. As we stare at it, we realize that it has every modern C++ developer's worst enemy in it. It has runtime polymorphism. It has virtual dispatch. So let's be true modern C++ developers and just refactor that away and replace it with the curiously recurring template pattern. Now we don't have an intermediate variant. We can actually send the richness of our types downstream, but once more we need to take a look at our implementation of message and refactor it to take advantage of this. Rather than accepting a variant, we make it templated on the actual type. Instead of visit and overload resolution, we use an if context for cascade. We head back to the profiler, and we find that the runtime is now comparable to the original. But we didn't just walk away from this with a better performing application. We also walked away with a lesson. We walked away with some real world experience. The next time someone says to us, don't worry, I'll get quickness for free because I'm using C++11 move, we can look at them and we can say with confidence, there ain't no such thing as a free lunch.